This is EE698I, Mixed Signal IC Design, and this is lecture number 5. In the last class, we were discussing about how to measure the SQNR, that is the signal to quantization noise ratio of an ADC. So let's say this is the ADC we have. Inside we have the sampler and the quantizer. Okay. So what we do, we give a sinusoidal test signal, which I called U. So the output V will be the input plus the quantization noise. And what we do, we take the power spectral density of the ADC output. And this power spectral density was in turn defined as the Fourier transform of the autocorrelation function. But we saw that in practice, we can get a good estimate of this PSD by taking the magnitude squared of the Fourier transform, dividing it over the observation interval, and taking multiple averages of it. Okay, in the discrete time, similarly, we have 1 by n times mod x of omega squared averaged. Right? We also observe that for real signals, this power spectral density is an even function of frequency. So let's say you take a discrete time power spectral density. So between minus pi to plus pi, it's an even function. So it might look something like this. Okay. So this is a two-sided power spectral density. In practice, instead of showing both the positive and the negative frequencies, we will show only the positive half. So what we'll do is we'll take this negative half, fold it over, and add it to the section, and say that now this is my one-sided power spectral density. Oops, let me draw it more properly. It will look like this. Right, so if this was, say, some P0, this will be 2P0. Right, so this one-sided PSD is essentially 2 times that of the double-sided PSD. We also notice that we can calculate the power of the signal by taking the area under the power spectral density curve. Right, so we integrate the power spectral density over the entire frequency range. And for the discrete time signals, we have the scaling factor of 1 by 2 pi, 0 to pi, power spectral density times d omega. Okay. And since here we are integrating only from 0 to infinity, so this is essentially the one-sided power spectral density. Same with this. In the last lecture, I think there was some confusion in some of the steps I used to derive this result, especially the way in which I dealt with impulses. So let me clarify them first. Right. So here, when I mentioned that the strength of this impulse is this value P0, that is A0 square by 2, what I really mean is the area of this impulse. Okay. So similarly, when I write here that the power is the power spectral density value at F0, what I actually meant was that this is the area of this power spectral density, right, around this F0, okay, around a small frequency range around F0, in a small frequency range around F0, the area. Okay, similarly, in this case where we have two sinusoids, so what this actually how this should have been properly written is that this is the area around F0 plus the area around F, right? So finally, when you have continuum of frequencies like this, the overall power will be the entire area under this curve. Okay. Okay. And next, we also saw that for the quantization noise, along with the existing already made two assumptions, which were the quantization noise is a random signal and that it has a uniform probability distribution. We made an additional assumption, which was that the power spectral density of the quantization noise is white, right? That is, it has a flat power spectral density. So if we look at the power spectral density from 0 to pi, this is SQ of omega, it's going to be flat, right? And we know that 1 by 2 pi area under this power spectral density is equal to delta square by 12. Okay. So what we do, if we for the ADC, then we give a sinusoidal input and we take the power spectral density of the ADC output. So what we'll have is the following. So let's say this is pi. This is the power spectral density of the output. Okay. So what we'll have is an impulse corresponding to the input sinusoidal frequency. And for the quantization noise, we'll have a flat spectrum like this, right? So the strength of this impulse, that is the area of this impulse, gives the signal power, and the total area under this entire curve gives the total power of the signal plus the quantization noise, right? So if we take the total area under this curve and subtract the area of this impulse, we'll get the quantization noise power. So we can find the signal to quantization noise ratio. And from this, we can calculate what is the effective number of bits using this formula. Right? Okay. So now let's see how should we choose the frequency for this input sinusoid. Okay. So if you remember a couple of classes ago, we saw two scenarios. In the first case, we took an input sinusoid, continuous time signal with a sinusoidal frequency of 201 Hertz, and we sampled it at a rate of 1 kilohertz, that is 1000 Hertz, right? So this resulted in a discrete time sequence U of n of cos 2 pi times 201 times n by 1000. Okay, and when I took 1000 samples of this, fed it to a quantizer and observed the quantization noise, like a histogram, I found that the distribution was uniform, right? And for the second case, I chose a frequency of 200 Hertz, had the sampling frequency same as 1000 Hertz. Right? In this case, what is the discrete time sequence I get? It is cos of 2 pi times 200 into n by 1000. So this simply reduces to cos 2 pi into n by 5. Okay, and we saw that when we took 1000 samples of this sequence, the quantization noise did not have a uniform distribution, right? Why? Well, because this sequence has a period of only 5 samples. Okay, so even though you took 1000 samples, it had only 5 distinct or 5 unique values. Whereas here, this signal has a period of 1000 samples, right? And so there is no repetition within these 1000 samples, right? All 1000 samples are unique. Okay, so to characterize the ADC, we need to choose a sinusoid which is of this form, right? Because we don't want to feed the same samples again and again, because we are not getting any new information, right? Because here we had only 5 samples, we kept feeding them again and again for 1000 samples, right? That is like till we get total of 1000 samples, right? So what's the bottom line? We need to choose a sinusoid such that if we want to say process n samples, which means the sinusoid must have a period of n. Okay, and how should the sinusoid look like then? So U of n must be cos of, so okay, let me write it in the next page. U of n is cos of 2 pi into m by n times n, right? And m and n should not have any common factors, right? Like for example, if we choose m as 200 and n as 1000, we see that because they have common factors, they get cancelled out and the overall period reduces, right? And the only if I have it as 201 or something, the period remains 1000, right? What it means, m and n must be co-prime. Okay, so if u of n is this, what is the corresponding continuous time signal? Well, u of t is cos of 2 pi times m by n. Well, to get the discrete time sequence from the continuous time signal, we replace t by n ts, right? Now to do the inverse, what do? We replace n by t by ts, that is t times fs, right? So that's what we do. We replace this n here by t times fs. So this simplifies to cos 2 pi times m by n times fs times t. Okay, so what is the equivalent continuous time frequency? It is m by n times fs. In other words, the ratio of the input to the input frequency to the sampling frequency must be of the form m by n, where m and n are co-prime. Okay. Well, we'll see that choosing a signal which is of this form has some other advantages in characterizing the ADC, which we'll discuss in a later class. Okay. So what we finally need to do is that we need to feed a sinusoidal signal to the ADC, and we need to make sure that the input frequency of the sinusoid satisfies this condition. Okay. And at the output, we take the power spectral density of the ADC output. And how is this power spectral density computed? We know that it's computed as 1 by n times mod x of omega squared average. Okay. However, it turns out that there are some practical problems in computing this Fourier transform. Okay, let's see what they are. So first of all, what is this transform? It is the discrete time Fourier transform, right? So how is it computed? Well, we know x of omega is summation n equal to minus infinity to plus infinity x of n e power minus j omega n, right? So let's say signal x of n has a discrete time Fourier transform like this, say from minus pi to pi. Okay, or let's say I'm considering it from 0 to 2 pi. Okay, so let me erase this portion. Right, so this is 2 pi. Okay, so the first problem is that, well, if we observe this frequency variable, that is omega, it is a continuous variable, right? So it can take any value from 0 to 2 pi. Okay, so to find this discrete time Fourier transform, we need to do this computation for all values of omega from 0 to 2 pi. This obviously is not possible to do in practice, right? So the first problem is omega is a continuous variable. And it can take any value from 0 to 2 pi. Okay. And the second problem is that if you look at this summation, okay, the limits go from minus infinity to plus infinity, right? So which means that we need to record this signal for infinitely large number of samples, right? This again is not practical, right? Well, in some cases it might be okay, especially where the signal x of n itself is limited to say some p samples. Okay. In that case, the summation limits will change to n equal to 0 to p minus 1, right, for those p samples. But for periodic signals such as the sinusoidal signal, which is what we are feeding it to our ADC, right? So it is a periodic signal, right? So it exists from minus infinity to plus infinity. And obviously we need to do this computation over the entire limit. Okay. So these two are the problems, and see how we go about solving them. Well, the first problem is that from 0 to 2 pi, we need to compute the spectrum, okay, for all values of omega. And obviously we cannot do that. So what we do, we'll say that we will compute the spectrum at only a fixed frequency points. Okay. Well, if you think about it, this is very similar to the problem we had with continuous time signals, right? So with continuous time signals, we saw that we cannot store them easily because we need to store their values for all possible values of time, right? So that's why what we did, we decided to store or decided to process them at some discrete time instance by sampling them. Okay, so essentially we'll do the same thing here as well. Okay, so let's say we decide to take or compute the spectrum, compute the value of the spectrum at only n points. Right, so we have a total range of 0 to 2 pi to cover, and we decide to take n points within this. So as any sane person will do, we will take uniformly spaced frequency points. So it will be 0, 2 pi by n, 4 pi by n, and so on till n minus 1 into 2 pi by n. Right? So essentially the continuous variable omega is now replaced by a discrete variable k times 2 pi by n, right? Because these are the frequency points at which we are calculating the spectrum. Right? And how what is the value of k? K can take values from 0 to n minus 1. Okay, so this solves our first problem. How about the second problem? Well, obviously we cannot record the signal, record the output for infinitely large number of samples. So what we do? Well, we will say that we'll record it only for, say, a total of NR samples. Okay. So this NR will be our record length. Right? So with these changes, let's see what happens to the equations for the Fourier transform. Okay. So first let's write the original equations for the discrete time Fourier transform. So x of omega is summation n equal to minus infinity to plus infinity x of n e power minus j omega n. Okay, let me also put this here. Push it up. And the inverse transform is this: x of n is 1 by 2 pi integral from 0 to 2 pi x of omega e power j omega n d omega. Okay, so what we do here, first we'll replace omega by this value k times 2 pi by n. Right, so what this becomes x of k 2 pi by n. Okay, so this essentially is a frequency, is a function of k, so I'll just write it as x of k. Right, and this is equal to what? Summation. Again, we have decided that we are going to record only NR samples. So the summation will range from 0 to NR minus 1. And then we have x of n e power minus j. Again, we'll replace this omega here by k times 2 pi by n. So we have k times 2 pi by n times n. So similarly, the inverse transform, we have this, so 1 by 2 pi, right? Now, instead of integration, we'll have a summation, right? Because omega is no longer a continuous variable. So we'll have summation, okay? And now, what is the thing that is varying? We have only k that is varying, right? So we'll vary k from 0 to n minus 1, x of k e power j 2 pi by n times k times n. And what is d omega? Well, we are incrementing in steps of 2 pi by n, right? So d omega is essentially 2 pi by n. So this simplifies to 1 by n summation k equal to 0 to n minus 1 x of k e power j 2 pi k n by n. Okay. Well, at least from this equation, it looks like there is no constraint, or there did not be any relation between this nr and n, right? So nr is the number of samples for which we have recorded the signal, and n is the number of frequency points, right? But before jumping to that conclusion, let's actually take a look at this equation. Okay, so let me first copy paste it. So this is x of n, right? So let's compute what is x of capital N plus n. So remember, this n is the number of frequency points, right? And what is this? This is 1 by n summation. I'll just write as k, x of k e power j 2 pi k by n times capital N plus small n, right? And what is this? This is 1 by n summation over k, x of k e power j 2 pi k plus 2 pi k by n times n. Okay. So if I just simply expand it, I'll have x of k e power j 2 pi k times e power j 2 pi k by n times n. And we know that this is equal to 1, right? So this finally reduces to summation k x of k e power j 2 pi k n by n. And what this is equal to? This is simply equal to x of n, right? So what do we see? X of n plus n is same as x of n, right? So what this says is that if we take a sequence x of n, find its Fourier transform by taking only n frequency points, okay? And let's say you try to reconstruct the signal back from this x of k. And what you will find is that in the reconstructed sequence will be periodic with n. Right? Well, one way to understand this is as follows. So when we took a continuous time signal and sampled in time domain, okay, and let's say the continuous time signal had a spectrum like this, right? After sampling at a frequency, say fs, what we saw was that the spectrum got repeated around multiples of fs, right? So which means when we sample in time, we have some kind of a periodicity in frequency domain, right? So let me quickly erase this. Here what happens? What's happening? We are sampling in the frequency domain, right? Because we are doing, what we are doing is we are taking the samples of the discrete time Fourier transform. Okay, so here sampling is happening in the frequency domain, which means we should expect some kind of periodicity in the time domain, right? And that's what happened. Okay, so what this means is that if we take a discrete time sequence, okay, so let's say it is something like this. Again, this is a discrete time sequence. Only for the sake of simplicity, I'm showing it like a continuous time signal. Okay, let's say this is 0. This is my last sample, nr minus 1. So which means the record length is nr. Okay, so I compute the spectrum at n frequency points. And from this n frequency points, I try to reconstruct the signal back. So what I'll get is the following. I'll have the same signal, but I'll also have a periodic repetition of the signal again. And this period will be n, right? And this is my total of nr samples. Okay. So what this operation, that is computing the spectrum at n points, n frequency points, does is that it assumes that we have this kind of a periodic signal and it computes the spectrum of this periodic signal. Okay. So in this case, what I did, I've chosen the number of frequency points to be greater than the record length, right? So let's see what happens if I choose the number of frequency points to be less than nr. So what will happen if I do the reconstruction? Well, I'll have the same thing. I'll have the signal getting repeated repeated after n samples. But in this case, if this is my total of nr samples, n is less than nr, so I'll start having repetitions from here itself, right? So what's happening? Well, in this case, we clearly see that the initial and the last few samples will no longer be the same, right? They'll get changed compared to the original signal, right? So this is similar to aliasing that happened in the when we sampled a continuous time signal to convert it to a discrete time sequence, right? The same thing is happening here. Okay, so let's take a look at an example. So here I'm considering a discrete time sequence, and there are total of 12 samples from n equal to 0 to 11. So my record length NR is 12 samples. Okay, so what I'm going to do is I'm going to compute 10 frequency points. That is, compute the spectrum at 10 frequency points. So n is 10. And from these 10 frequency points, I'm going to try to compute the signal back. Okay, and what do we expect? Well, there should be periodicity after 10 samples. So the same ramp should get repeated after 10 samples. So here I'll have this ramp going like this. So similarly, I'll have the last two samples, something like this, right? So what will happen? These two get added up. These two samples get added up. So similarly, these last two samples will also get changed, right? And that's exactly what has happened, right? So the samples in red, they are the ones that we get after reconstruction, and the ones in blue are the original, original samples, right? So from this discussion, it is obvious that this is not a viable choice, right? We cannot choose the number of frequency points to be less than the record length we have. So obviously, this is the other option. We need to choose n to be greater than or equal to nr, right? This is totally fine. But if we choose n to be greater than nr, what happens? The other samples are inherently assumed to be 0, right? So we are essentially wasting out information, right? So instead of filling it zeros, we can indeed fill these, like in between samples with the input signal itself, right? So we can choose n to be equal to nr. Okay. Well, the other way to look at it is that in practice, when we are dealing with sinusoids, what we'll do, well, probably we'll capture one cycle of the sinusoid, right? Something like this, right? And we'll try to compute the spectrum. And we want the signal to be assumed as a periodic signal. So we want this portion, right, to be repeated just after this, like this, right? Only then we'll have a continuous sinusoidal signal, which will be periodic, right? So what we need to do, we need to choose n to be nr. Okay, and that's what we do in practice as well. Fine. So with this choice, so let's see what happens to these equations. So let me just copy them. So this is x of n. So what has changed is we have nr to be equal to n, right? So this changes to n minus 1. Okay. And this is called the discrete Fourier transform. And this is what we use in practice to compute the frequency spectrum. Okay. Well, the other one was called discrete time Fourier transform because we were dealing with discrete time signals, but the frequency variable was still continuous. But here, even the frequency is discretized, right? So it's a truly discrete Fourier transform. Okay. So what happens in a discrete Fourier transform? Well, we are taking the x of n. We are recording it only for n samples, right? And then finding the discrete time Fourier transform of it, and then sampling it, right? And this act of limiting this, that is this recording the signal x of n for n samples, can be thought of as multiplying the signal x of n with a signal like this, right? So it is 1 from 0 to n minus 1, and it is 0 for all the other samples, right? And this is called a rectangular window, right? And I'll say it's rect of n to symbolize the fact that it has a total of n ones. Okay. So what we are doing, we are taking the discrete time Fourier transform of this signal, x of n times rect of n, and then sampling the discrete time Fourier transform of this, right? Okay, so DFT is nothing but sampled discrete time Fourier transform of x of n times rect of n, or I should say an n-point DFT, right? So n-point DFT signifies that we are taking n points in frequency, right? And in practice, there is no restriction to choose this value of n. We can choose this n value to be anything. But some smart guys like you had figured out that if n is chosen as a power of 2, say it's some 2 power L, then this DFT operation can be computed more efficiently using some algorithm called a fast Fourier transform, right? But in the present day, with the kind of computation power we have, this is no longer a problem. We can choose n to be anything, but just for legacy reasons, we still continue to choose n to be a power of 2. Okay. So in a discrete time Fourier transform, we had omega that was ranging from 0 to 2 pi, right? And the spectrum was symmetric around pi, right? Something like this. Okay, and in discrete Fourier transform, what we do, we discretize the frequency axis, right? And then this is 0. So this is n. So I'll have discrete values from 0, 1, 2 till n minus 1, right? And obviously, just like discrete time Fourier transform, this will also be periodic around n by 2, right? We'll have something like this. Okay, and these points, these discrete frequency points, okay, these are called frequency bins. Okay, and each frequency, that is say a kth frequency bin, it corresponds to a discrete time frequency of k times 2 pi by n, right? And how does it translate to a continuous time frequency? Well, we know 2 pi corresponds to the sampling frequency, so this is simply k times fs by n. Okay, so let's get back to how we calculate the power spectral density, because that's what we want finally, right? So we saw that we compute power spectral density. Initially, we used to compute it as mod x of omega squared by n, and we took multiple averages of it. Okay, so that's assumed, right? So now we are not computing this discrete time Fourier transform x of omega, but instead what we are doing, we are computing x of k, right? The discrete Fourier transform, x of k. So how should we compute the power spectral density? Well, it is mod x of k squared by into 1 by n, right? Again, we'll average it multiple times. So let's call this a function of k, fine. And how did we compute the power earlier? Power was computed as 1 by 2 pi, integral minus pi to pi, or it can be from 0 to 2 pi, right? The power spectral density as a function of omega. This is what we did initially. Again, notice that since I am going from 0 to 2 pi, this is a two-sided power spectral density. Okay. And now how this equation now transforms to, well, this is 1 by 2 pi. Integration will now become summation, and the variable is no longer omega, it is k, right? So k goes from 0 to n minus 1. It is power spectral density as a function of k. So function of k. So this should also have been a discrete function, right? Function of k. And we have d omega, and d omega is 2 pi by n, right? That's the frequency step we take. So and this simplifies to 1 by n times summation k equal to 0 to n minus 1 power spectral density as a function of k. And we know that this is computed, right, as this, right? So let me substitute that. So what I'll have, k equal to 0 to n minus 1 mod x of k squared by n. right? So again, this is averaged multiple times, so that's assumed. So what I get, 1 by n squared, k equal to 0 to n minus 1, magnitude squared of the discrete Fourier transform, and we take multiple averages of it. Okay. So to compute the power, what we have to do, we need to take the discrete Fourier transform, take the mod square of it, and then sum it up, and then divide the result by n squared, right? And in practice, if you are interested only in the ratio of powers, like how we are interested in the ratio of the signal to noise power, I mean, sometimes we can ignore the scaling factor, right? Because the scaling factor is going to affect both the signal and the noise power by the same amount. So, just for the sake of this calculation, ratio calculation, you can ignore the scaling factor, right? But for computing the absolute power, that is the exact value of the power, you need to take care of the scaling factor. Okay. And in MATLAB, this entire business of computing this power spectral density, right, using the Fourier transform, using the discrete Fourier transform, can be done in a single command. And the command is pwelch. Okay. So what this command does, it computes the Welch estimate, that is, it averages the mod square Fourier transform, that is mod square x of k, right? So let's say you want to take an endpoint DFT, right? So what we do is, since we want to take multiple averages, let's say take more number of points. So for example, as we saw in the last class, let's say we take a total of 4 n samples, right? We'll divide it into 4 segments. Each segment will have a total of n samples, right? And what we can do is we can choose this as the first segment, compute the DFT as mod x of k square, right? And we can choose the second segment by overlapping some samples from this, right? So we can take second segment like this, third like this, fourth like this, fifth like this, right? So in this way, we can get 5, like different segments. And for each segment, you can compute what is mod x of k squared by n, right? And you can take average of all of them to get the PST. And this process can be done in MATLAB using this command pwelch. Okay. We'll stop here and continue from the next class and see what happens when you take discrete Fourier transform of a sinusoidal signal. Okay, because sinusoidal signal is what of interest to us, and that's our test signal. Okay, so let's see what happens to that.